Okay, so what I wanted to do is to show you how to start from scratch and set up a model that is similar to the one we just saw, except this one will involve flow down a cylindrical tube, and the sides will deform as material is deposited. So we'll start with a 2D axisymmetric model, and what I'm going to do is just set this up. We'll have several different physics in here, but I'm going to start off with just doing one at a time. And so uh, generally everything revolves around the fluid flow, so we'll start with that. And I put in this laminar two-phase flow moving mesh. And if you can't find that, it's let me show you where to find that. Oops. It's it's in multi-phase flow right there, and down here, two-phase flow moving mesh. So use that one. And so we'll get this set up. We'll use a geometry that is in millimeters, and the geometry we'll use a rectangle, and we'll use pretty much the same diameter. So that was 1 millimeter aperture slot, so we'll have half a millimeter radius, and it was 5 millimeters long. And so we'll use that as the geometry. It's axially symmetric. And we'll put in some water for the fluid. I'm just going to use recent materials here. If I click on that, I use water all the time, so it's right handy. And add it. Okay, so with this interface, this simultaneously does the fluid flow and the moving mesh. And so we're going to have to put in 4 boundary conditions for both the fluid flow and for the moving mesh. Okay, so first of all, let's go do the fluid flow. This problem is familiar, so we can put in an inlet and an outlet. We've done fluid flow along a tube many times. We'll use Navier's slip for the outer boundary condition. So there's the Navier's slip, the inlet. Let's go bottom up for the flow. And so the inlet will use the laminar inflow boundary condition, and the fluid flow is 0.001 meters per second. And the outlet up at the top is just the default, which will be the pressure, no viscous stress condition. Okay, so we don't need a boundary condition on the inside because that's here with the axial symmetry. Now we've got to put in our boundary conditions for the mesh, and we'll have to put in 4 of those. We can't use the middle, we can't use the symmetry for the mesh boundary conditions. So we'll put in mesh displacement, and we'll put in the top and bottom boundary. And for that, we're going to fix the displacement in the z direction, but not in the r direction. And we'll put in another one of these, and we'll fix the displacement in the r direction, but not in the z direction. And then the last boundary condition we need is the mesh velocity. We'll prescribe the mesh velocity on the outer wall. This is the wall that will be moving as we have deposition occurring. And so what you want to do is select boundary system for the boundary here, and you'll get T1 for transverse velocity, and that we're just not going to specify. The normal boundary we will specify, and we'll just set it equal to 0 for now. Okay, so that should run. Let's take a look at the mesh. If we just look at the default mesh for this problem, it's really fine. And eventually we may want to use a mesh that's that fine, but while we're setting it up, I like to have a bit of a coarser mesh. Sometimes the coarse mesh or a coarse mesh can come back and haunt you because it'll cause problems with the model running. But let's see if this works. It should be okay. Oh yeah, I inadvertently put in that extra model, so I'm going to get that guy out of there. Just delete it out. And so let's try and run this. So the model runs, and here's the velocity distribution. So we recognize this velocity distribution, and also we recognize that there's something funny going on with the boundary condition here. Remember, we specified that this was a laminar inflow boundary condition, but pretty clearly that's not the case. It's a uniform flow rate condition. And so I'm not quite sure what's going on, but what I think is happening is when we have this laminar two-phase flow with the moving mesh, when we have the moving mesh, then because the mesh is moving, it doesn't allow that laminar inflow boundary condition to really be implemented. Okay, so nevertheless, though, this is the initial flow rate, and that seems to be just fine for a starting point. So let's go and put in the next one, which will be the transport physics. So transport of dilute species, and it's transient. And I'm going to go and change the dependent variable here. This is the concentration in the fluid, so I want to call it capital CF. And under the convection diffusion, I just want to make sure we're using the velocity field, and I'm going to now put inflow and outflow and a flux boundary. So inflow here at the bottom, and the rate coming in is 1. Outflow is at the top, and the flux boundary is the outer boundary. There'll be mass fluxing out across that boundary as the precipitation process occurs. And so we'll just set it equal to 0 for now. They'll specify the species CF, but set it equal to 0. And also the initial values, since we have a concentration of 1 coming in, I'm just going to set the concentration equal to 1 everywhere. Okay, so that should be ready to go. And let's see how it runs. I still have it set on just 1 second, so but the time is short, but it runs, and presumably we can run it for a longer time successfully. Now, at this point, I think what I'm going to do is go up here and put in a variable, and I'm going to just import these variables that I set up for the previous model. And you saw these are the same ones that I used in the previous model, and so rather than just have you have to read the screen and type it in, you can just import these, and that's fine to start with. Okay, so let's see, that's 2 of the 3 physics, and the model's running. So I think, as you're working through this problem, what would be good to do is, as you get each one of these physics, when you first get the flow working, you might just make a copy of the graphics here and paste it, and kind of keep track of your progress with some figures that are documenting how basically your progress. Okay, and so now let's put in the last physics. That's the reaction, surface reactions, and that's here under chemical species transport. There, it's a surface reaction, and we'll put that in. And what we need to do is just involve this outer boundary in the surface reactions. and we'll include a reaction right here, and that's specified for that boundary. And now I need to specify a term that's going to be the reaction rate for that species. So I've imported these variables, and this CS rate is the reaction rate at the boundary. We talked about that in the previous video, and so hopefully that's clear just what that term represents. Go and check out the previous video if it's a little fuzzy, but at this point I'll just assume that you know that what that equation represents and that you're okay with it. Okay, so this is where all the action is going to take place. I set the reaction rate for the surface reaction. This boundary in the transport model will be specified as a mass flux boundary. So there's the term, and I'm going to put it there. So remember, this is the mass flux. We're in the fluid and we have mass fluxing out across this boundary because it's being precipitated as a solid on the boundary. And then from a point of view of the fluid, it's as if it's leaving the fluid. So that's mass flux out. And from the laminar two-phase flow, the flow problem, we don't really change the boundary conditions. This is no flow along this outer boundary, even though it's moving. But we are going to change the boundary conditions with respect to the moving mesh. And we have a term that's called the growth rate, and we'll move the boundary, we'll move the mesh with the growth rate. So the prescribed mesh velocity is equal to the growth rate of the material that's being deposited on the wall. Okay, so I think it's going to work, except what we're going to need to put in is these terms called step 1 and step 2. We can't import those steps, so we're just going to have to enter them. Okay, so I put the step functions in. Step 1 is located at 0, 0, 2, and it goes from 0 to 1, and the transition zone is half a millimeter. And step 2 is at a location called threshold, and the rest of it is a default. And so I also put in, under the global definitions, a parameter called threshold that I set equal to 7. Okay, so if that's all done, then this should run. And I still keep it set for just 1 second because basically I just want to see if it runs okay. And you know, everything looks good. So now I can go and increase the time, and I'll try running this for let's just say e to the, say 5 e to the 5th seconds, and I'll do 50 values and see how that goes. Oh, I'm going to stop it since I'm kind of impatient. I want to get some feedback. Oh, actually, you know, we didn't have this transport turned on, so we're not really sure that this is working. Nevertheless, I'm going to go and turn on this plot so I can see what's going on. Plot group 1, and plot group 1 I'll have be a plot of the concentration CF. Okay, so let's check and make sure that the transport is working. Okay, so that's encouraging. We still don't really know that it's going yet until we see that start to change, but we can click here under progress, and so yeah, it started to run. We don't really know if it's going to run successfully, but at least it's going, so that's good news. And this is the kind of concentration profile that we expect to see early on. So there's a problem, and let's see. I think actually it just occurred to me that we didn't really check this. So if we go under laminar flow, yeah, so I'm not sure what the problem is, but I've had problems with this mesh smoothing type before. So I think Laplace smoothing works better, and let's try that. So look at that time. The time's just ripping along, and look, now the mesh is deforming, so everything is looking good. Okay, that's what we want to see. This seems to be behaving properly. We're having the wall come in as basically this material right here is a solid material that's been deposited, and the wall is building up and constricting the flow as a result. So let's take a look at the 3D plot group and see what that looks like at the end of the simulation. Okay, so there it is. There's how the open part of the conduit has changed. It necks down with this geometry, and you can see what happens to the flow as a result. Because the diameter has decreased, the flow velocity has increased. Because remember, what we're doing is fixing the velocity here. And so one thing actually that we might want to do is, what we're plotting here is the velocity, but let's also try plotting the pressure. If we do that, here's what we get. So there's a pressure 0.25, and if we turn back time, so when we started, the pressure right here is 0.16, but we're having a constant flow, and by the end of the run, the pressure is bumped up to 0.25, maybe even approaching 0.3. So it's close to doubled. And so one of the ways you can interpret this is, well, greater pressure or greater head loss through a pipe that's got some scale on it or clogging. Boilers have this happen. They get scale in the heat exchange tubes and have to be cleaned out, or a variety of other plumbing problems. Or if you have plaque built up in your arteries, then that restricts the diameter of the arteries, and it increases the pressure in the blood, and it is one of the things that leads to high blood pressure. And so we can think of this color here as a surrogate for blood pressure, and we see the response of the blood pressure to precipitation of some kind of a compound here on the walls. So that's all I'm going to show you. What I would suggest that you do is try to experiment around with this erosion factor. If you increase that term there, try 1 e to the minus 6. That'll increase the erosion. And actually, before you do that, what you might want to try is running it longer. And if you run it longer, then the walls will come in further, and then that'll be a bigger effect. And then you can try looking at the effects of limiting the growth by having the material be sheared off. Another thing that's instructive with these moving mesh problems is to be able to take a look at the mesh itself. So in the plot, if you go to here, so under the surface, if you plot wireframe, then you see the mesh here. And this mesh is looking pretty good. It's not really very deformed. But if you let this go further and this bulges in more and more, then the mesh will become increasingly deformed. and there may end up being numerical problems. What you can do is stop the run, and remake the mesh with this deformed geometry, and then continue it again. So that's always an option. So experiment around with this and try out various numerical experiments.